So that's the kind of rock that's at the actual center of the Little Rocky Mountains. It's an igneous kind of volcanic rock. All right? What it represents, I'm not sure. We'll have to dig into that a little more if you even care. But it might be kind of the same thing as Mount St. Helens, where you have magma coming up and it's cooling really fast, and it just gets stuck in the throat of something that could have been a volcano but never did. I mean, I know Devil's Tower is right near there down in Wyoming. I know there's some other structural things going on in the Montana, like the eastern Montana region, where you have these weird faults coming up. All right, you got to remember also the other types of deposits, like groundwater that's charged with these minerals, and it'll come up a fracture in, three-dimensional fracture in Earth, and as it's coming up that fracture, that pressure's dropping, and boom, it's starting to crystallize. That's how you get like gold deposits and stuff. Okay, hydrothermal deposits. So what you have essentially is a volcanic center of rock that was just frozen, and then you have two types of sedimentary rocks on the outside ringing it, okay, like a ring. Well, how did it get that way? This is where we have to think a little 3D, okay? And this is where I wish I had my diagram, but I can send you a diagram, no problem. You have these two sedimentary rocks that are generally flat lying, okay? And I'm going to represent those two as just my hand here. All right, this is on the middle imaginary line. I think it's limestone and sandstone. I'll have to check, but I think that's right. Well, at some point in there, this extrusive igneous volcanic rock started to push up, and it started to bow the crust of the earth like this, okay? And eventually it got like that. Now, if you imagine taking a brownie, like a big brownie sheet, out of the oven, letting it cool for like 5 minutes, and then go set it on the top of like your exercise ball, okay, those like 55 centimeter balls. What's going to happen when you set it on there? It's going to start to drape down on the sides, okay? The ball represents that mass of magma coming up and cooling slowly. Now, this doesn't punch a hole through it because it's so slow that it almost makes it's not so brittle. It's almost like a slow deformation, kind of like where I'm here, but different. So you get this warping like the brownie on top of the exercise ball. Well, when you do that, okay, when you do that, you extend the crust, and the crust of the Earth starts to expand, okay, because Earth is curved, and you're putting a curved object up against it and pushing up. It's going to expand. There's going to be expansion. When you get expansion up where it's brittle, up here at low pressure, atmospheric pressure, well, it's going to crack, and it's going to crack in like an X pattern, okay? And once you get cracks like that, then you have more places that this stuff can start to weather, and it's going to weather faster because you have a higher surface area. All right. If you have one face, it's going to weather in a road at some speed. Okay. If you have two faces, it's going to weather in a road probably almost at double the speed. But when you get edges in there, they weather really fast. All right. So you get the edges weathering, and you still have faces out here. That's why boulders generally get round. Okay, because you have points and edges and faces. Now, the faces take the longest, the points take the quickest, and the edges are somewhere in the middle. So what happens is you have all this weathering that's accelerated by the fact that it's broken up and you have a higher surface area. So this thing cracks, okay, as this magma comes up, these sedimentary rocks crack, and water starts to get down in there, and it starts to peel it away and just chew at it, and it basically breaches the top of this dome that's created in these sedimentary rocks, right? And when it breaches that dome, well, now you have these sedimentary rocks that are warped up. If this is the magma mass, and I'm only showing one side, okay? It starts to get warped up, and then now you have edges up here, and you get this kind of weathering, okay? It's almost like stair steps, okay? Where you have your sandstone and then your limestone on top, and then you have this mass of volcanic rock in the middle. And the reason why the volcanic rock sticks up higher than the other two, the sedimentary, is because it's just more resistant to weathering and erosion. It's called differential weathering is what it's all about. This hill, this mountain I'm standing on, over this valley, jeez, I did not fall that way, huh? This thing's standing here because of the same kind of thing. This rock is much, much harder than the stuff below it down in this valley. So you got these cliffs that drop right down. I mean, there's another cliff right down there. I go over, it's like 130 feet down there, and then another like 400 feet down at the bottom, okay? So, don't slip, alright? I think that makes sense. I know you got to kind of think about it in terms of switching from map view to cross-section view, but I can draw this stuff out for you, alright? But I think probably clicking your brain, if you just think about it for a second. Look at that diagram though, and it'll make sense. When you're looking straight down in the middle, you're looking through the sedimentary rocks. It's almost like a window through them. And in the middle is this really resistant volcanic rock, okay? And that's what creates the high parts. And then you have this draping, three-dimensional kind of draping dome that comes up. And you've got two types of sheets of rock that go all the way around. And then there's some faulting and stuff that's going on. You can see that on the map. On the map, what's cool about the map is I think I mentioned it's a big PDF. It's like 4.5 megabytes, but you can zoom way in on it. And what you can do is you can maybe even mentally overlay the trails, like if you have a trail map, or if you can scan it or take a digital photo, put it to me, I'll overlay it on there. What I'd like you to be able to do is take away is when you're hiking there, you can probably pinpoint where the trail crosses a difference in geology, like from a sandstone to a limestone, or a limestone to a volcanic rock. And what you should try to do is, see if there's a change in the landscape or the character of the way things lay, or the color of the rocks. Now, bear in mind, a line on a map is 1 plotter pen width thick. It's very thin. On the ground surface, it might be 400 or 500 feet wide. Alright, just when you scale it up, it's just a limitation of mapping. Right? When you go to print, you got to print it at some width so you can see it, but at scale, it's huge. Contour lines are the same thing. They're generally about, I guess it depends on the map, but I've heard anywhere between 50 and 200 feet wide when you scale them up on the ground surface. So it's not like you're going to like, oops, wow, everything's different. You might have to go over some ground before you start to notice it. Hey, over there it was like this, but up here it seems to be more like this, and those rocks were sandy, and these rocks look more like they have shells or whatever in them. And then when you get to the volcanic rock, well, that should be obvious. Volcanic rock tends to have some more iron in it, probably have more iron in it. It should have a rustier colored look. I think the report said, I'll have to check that. I think it said it had much more iron oxide in it, so it's going to look like a reddish, kind of brownish, orange maybe. And you should see that. And you could probably be able to take and find 3 samples of each one and smash them open with a hammer once you get home and look at the unweathered surface, okay, the stuff on the inside that hasn't been exposed to all this rain and snow and ice and hot and cold, hot and cold, hot and cold for millions of years. Now, I think they said that the sandstone was 250 million years old, which puts it around Permian time, which is about the time that the end of the Paleozoic period happened, okay? The Paleozoic era, which was ancient life, Paleozoic. That's when you had a lot of ocean life, okay? It went into the Mesozoic era, okay? And that was middle life, Mesozoic, alright? So it's right around that break point, because all the stuff on that geologic timescale is roughly based around fossils and where they disappear. Okay, and there was the biggest, largest mass extinction that we think we know of now, based on the available fossil record, happened right at that boundary between the ancient life and the middle life, between the Paleozoic and the Mesozoic era. It's called the Permian-Triassic boundary, okay? Like, a ton of life disappeared in the sea all of a sudden. I mean, it's literally like all teeming with all these fossils of all different kinds of variety, and then all of a sudden, they stopped. And only a small percentage of them came through and re-radiated and got their variability again, but it really whacked down the population of all these different kinds of clams and mollusks and all these weird things that there was just a ton of at the time, okay? And then the Mesozoic is when all the dinosaurs and the land creatures started to emerge, and the plants and the bees and all that stuff, the flowering plants and the bees, to pollinate and all that. And you saw, I think, a lot more complexity rather, in like some of the predators in the ocean, like the sharks, okay? And the mammals were in there, but they were like these weird little things. And then blammo, something happened there at the end of the Mesozoic leading into the Cenozoic, recent life, okay? And that's when the dinosaurs became extinct. And I think that the limestone is in the Mesozoic era. I'm going to have to check the report. I don't have it with me, but I think the sandstone is Paleozoic, the limestone is Mesozoic, and then the very, very youngest rock is that volcanic rock that came up after both of these were around for a while. Okay? So it's kind of cool. The youngest rock is in the center of the mountains when you look at it in map view. Alright? Whereas the, I think it goes the youngest, oldest, and there's a ring of them, of the oldest, and then the middle ones. So you have the oldest, the middle, and then the youngest come up like that. And that's what the volcanic rocks are. I think that's it. Again, thanks. Any questions, just ask me. Obviously, I'm just blowing through this, really talkative, but I wanted to keep it kind of qualitative and not quantitative with all the fancy names and chemicals and all that. If you want to know about beach sandstones, okay, and how beach sandstones ask, all right, because that's a critical thing that I don't see talked enough about in geology, unless you like go way down into the nooks and crannies of one of the subfields called sedimentology and stratigraphy, which not many people do. They just want to go hiking and check out the cool rocks. Anyways, that's it. Again, the links will be below, and just fire away any questions. Anybody that sees this, I might put this on my blog, so anybody have any questions, you can either comment on the YouTube and I'll carry it over to the blog, or just hit the comment thing below. It might ask you to give an email. That's fine. It's cool. Don't worry about it. Everything's good there. You got to do it to comment, though. That's so I don't get robots on there. So, thanks for the time, and we'll see you around. Appreciate it.